So we're going to talk a little bit about the periodic table. The periodic table has not always existed. Originally, people had discovered different elements and we had information about them, but there was no real organized way of presenting them. So in 1869, Dmitri Mendeleev was looking for patterns in the elements, and he found that if he put them in order of increasing mass, there were patterns that repeated, kind of like the notes on a piano keyboard. So hydrogen and fluorine and chlorine had some similar properties, and helium and neon and argon. And he thought, well, this is really interesting. And so that's known as the periodic law. When the elements are arranged in order of increasing mass, certain sets of properties recur periodically. So he organized the elements that they knew about into a periodic table, and he arranged the things in rows so that the elements with similar properties were in the same row. And so this is just looking at the first 20 elements. So he ordered them like this so that lithium, sodium, potassium are on top of each other. And these guys are on top of each other because they have similar chemical properties. So when he put together all the known elements, there were some gaps in the table. And he predicted that elements would be discovered to fill in those gaps. And he even predicted their properties like density remarkably accurately. So this is just kind of interesting. This shows time of discovery. And so in 1869, some of these darker purple were still not discovered when he did his periodic table. And this is how, in 1869, Dmitri Mendeleev completed the first periodic table. Does anybody even know what the game Tetris is anymore? Okay. I just thought it was humorous. It never gets a laugh, so it's fine. In our modern periodic table, instead of increasing mass, they are ordered by increasing atomic number. And our modern periodic table has more elements, of course, because more have been discovered. So there are parts of the periodic table. So here we've used some colors to shade in different areas. So all of these yellow elements, those are all metals. And all of the green ones are nonmetals. And then the ones that kind of are in between here, those are metalloids or semi-metals. And so you should know that the nonmetals are in the upper right corner and that the metals are in the lower part and to the left. And the semi-metals, they're kind of metal but kind of not. They're in between. How do you remember which side is which? Well, take something you know something about, oxygen. Is oxygen a metal? No, it's in the air. We're breathing it. Okay, so this is the nonmetals. Or you could look at something like copper. Is copper a metal? Yeah, so this area must be copper. Here are some descriptions or some characteristics of these different groups. Metals are good conductors of heat and electricity. They're malleable. You can hit them with a hammer and smash them flat. They're ductile. You can draw them into a wire. They're often shiny. And what's most important for us is that they tend to lose electrons when they undergo chemical changes. Nonmetals are kind of like the antimetals. They're kind of all the opposite things. They're poor conductors. They're not ductile. They're not malleable. And they gain electrons. The metalloids or semi-metals, kind of mixed in between. Some of these are classified as semiconductors, and you've probably heard about those. Those are very useful in electronics because they have an intermediate electrical conductivity, And that conductivity is highly temperature dependent. And so you can do some really cool stuff with semiconductors. So here is another periodic table showing some different groups. So here we have the yellow ones, the two columns that stick up over here, and the ones over here, the columns that stick up. And together, those are known as the main group elements. These guys down here are called the transition elements. And I kind of like the color here because this kind of looks like a sandy bank, and this is a river, and here's another sandy bank. This is the transition between them, if that helps you to remember. And then we have group numbers, and we have periods. Periods are rows. Let's just write that in. And group numbers, the groups are columns. So the rows, the periods are just numbered 1 through 7. The group numbers are a little bit funky. So there's one way of numbering them that is just 1 through 18, and that's what the International Union of Pure and Applied Chemistry says is the official way to number them. But then there's also a numbering that has A's and B's in it. And I prefer that. That's what Americans typically use. And there's some useful things about those group numbers. You'll notice over here, this one's numbered 13. The other one is 3A, right? So you take off the 1, and it's the same number. 4 is 14, and 5 is 15. We don't really deal with the group numbers of the transition elements at all. So elements in the same group have similar properties, and there are a few groups that have special names. And these are things that you should know. So the noble gases are group 8A. So in the periodic table, that's the far right column: helium, neon, argon, etc. Those are all gases, as the name implies, and they're very non-reactive. At the far other end of the periodic table, we have the alkali metals, group 1A. And these are things like lithium, sodium, potassium. Those are metals, and they're very reactive. And then next to them, we have the alkaline earth metals. Those are fairly reactive, but not as much as the alkali. And then back to the right side again, the halogens are group 7A. That's fluorine, chlorine, bromine, iodine, those guys. So any of the metals that are in the main group, they're going to lose electrons because that's what metals do, but they're going to lose their electrons quite predictably. So those main group elements, most of them form cations with predictable charge, and the charge is just equal to the group number. So that's kind of convenient. Can't remember. So these guys in group 2, they form positive 2 ions. Aluminum's over here in group 3. Group 3A, it forms a plus 3 ion. And that's why 3A is a little more useful than 13. The nonmetals, they gain electrons. So the metals are going to become cations by losing electrons, and the nonmetals are going to gain electrons to become anions. And they do this so that they end up with the same number of electrons as the nearest noble gas, which that might not be all that helpful. And this might not be that helpful either. Another way to think of it is the charge is equal to the group number minus 8. But I'll get to a way that you'll probably like better in a minute. And then the transition elements, they do all kinds of crazy things. So in general, the alkali metals, the guys in group 1A, are going to form 1 plus ions. Group 2A, the alkaline earths, 2 plus ions. The halogens are in group 7A. They are one step over from the noble gases, right? So fluorine, we learned that the number 9 tells us there's 9 proteins. 9 9 protons. In a fluorine nucleus, how many electrons does fluorine have then? 9. Okay, so right next to it is neon. How many electrons does neon have? 10. So when fluorine becomes an ion, it gains 1 electron so that it has the same number of electrons as neon does. And you can also look at that as group number minus 8, so that's group number 7. 7 minus 8 is -1. And then we have the oxygen family. If it has a special name, I don't know what it is. Those are in group 6A. They tend to gain 2 electrons and form 2 minus ions. So you can see oxygen right next to fluorine. Oxygen has 8 electrons. And so everybody wants to look like the noble gases, so they're going to gain or lose electrons so that they look like a noble gas. Right? So oxygen is going to gain 2 electrons that have a 2 minus charge. So here are the noble gases. They pretty much don't react. They don't make ions at all. So here's group 7A, and these guys are going to form -1 ions. In group 6A, -2, and group 5A, -3. So group number -8 works, but what's a little more fun is, let's pretend we're playing a board game, and we're going to start over here, and then we're going to move backwards, right? So if I want to know what charge phosphorus has as an ion, I'm going to start over here and count backwards. -1, -2, -3. And so that's how you predict the charges of non-metal anions. It's just how many squares over from the noble gas are they? And these guys over here, just the group number tells us what the charge is. And then there's aluminum. Aluminum is in group 3A. I feel like I'm missing something. I guess we don't need to talk about that yet. Okay, so we should be able to do this. Predict the charges of the monatomic ions, that just means single atom, formed by these main group elements. So nitrogen. We got to find nitrogen on the periodic table. -3. Yeah, so nitrogen's over here. And so we're going to start here and go -1, -2, -3. And so if we write the symbol for that ion, it's going to be N with a 3 minus charge. We put the minus after the 3 so it doesn't look like an exponent. We don't want people to think that this is a variable, capital N raised to the -3 power. How about rubidium? +1. Great. So rubidium is over here. It's one of the metals, right? These guys are going to gain electrons. And so this is going to be Rb with just a plus. Now, if you wrote 1+, it's okay. But this is one of those places where I think chemists decided if it was 0, we wouldn't put the plus. If it was more than +1, we'd put a number, 2+ or 3+. So let's just not write the number 1. So that's how it goes, sort of. But here, this is in group 1A, and so that's its charge. Any questions?